Okay, let's get started. So our speaker today is our own Professor Joaquin Vieira. If you look at Joaquin's LinkedIn page, it'll tell you he's done things like won the Sloan Foundation Award and the Antarctic Service Medal and built the South Pole Telescope. He's also, of course, responsible for building the Center for Astrophysical Surveys, where you folks are at right now. And we have personally gone in front of associate deans and argued for important things like grad student funding for fellowships and CAPS postdoctoral funding and the money that is being used to stuff your faces with pizza right now. So it's an absolutely critical role that Joaquin is playing in the department. His experimental work on cosmology with the cosmic microwave background is well known. You can even read about it on Wikipedia. Or you can pay attention to him today in his talk. Joaquin, please.
Thank you, Gavin. So it's a real pleasure to be here. Really proud of all of you in the room as an alumni. This is the new logo that Spencer did behind you. And I found out recently, okay, so like I always do the SB shirts, but I always sketch it out and then send it to a professional, my old college roommate. But this, and I assumed Spencer did the same thing. Like she probably had some concept and sketched it out and sent it to a professional. But I found out last night she did this in Microsoft PowerPoint. No, Paint. Paint. A free online paint program. So I was actually even more impressed then. I love the design. I think it's great. Okay. So I'm going to give like a kindergarten level of things I do and just kind of a survey and things I'm excited about. Feel free to interrupt and ask questions. Nothing's going to be too like heavy or complicated. So the too long didn't read is CMB is an observational foundation for our current cosmological model. And CMB surveys are now sensitive enough that we're doing important work in astrophysics. And recently we've opened up the millimeter transient sky. So I think another way of saying that is like, in the past, it's been cool. We've understood like our cosmological framework from CMB. But in the next 10 years, I think we're going to transition to like people in the room starting to use that data like a normal survey more than been done in the past. The next generation survey is real. It was endorsed by the ASTRO 2020 Decadal Report and the recent DOE P5 report. And it's gone through DOE CD0, which just means it's now a real project. Don't worry about the acronym. Conceptual design 0, stage 0. The way I think to think about this is we all know about Vieira Rubin Observatory and LSST, and that's like $1 billion class, takes a decade to build, joint between DOE and NSF. And this is the next survey after that. Again, 50-50 between DOE and NSF, $1 billion class, and this will be kind of the next decade. In DOE speak, stage 4, effectively, I call it $1 billion class. But in DOE, it's like the real experiment, whereas everything else is like stage 3 and kind of done at the university level. This is now like national lab scale. Okay, so then what I'm going to set the stage, but then I wanted to think about, we were kind of actively building and designing this right now, actively designing and soon to be building. And I'm already thinking about kind of what comes next. And there's a few directions to go after this. One is higher spatial resolution, which means even bigger dishes than South Pole Telescope, shown here. Others are higher spectral resolution, so rather than doing imaging, doing spectroscopy. And the other would be higher time resolution, but I'll briefly touch on that, not a lot. Okay, so over the last kind of 20, 25 years, our measurements of the cosmic microwave background have become more precise. And here you see like the march of technology and sophistication going from 92 to 2013. One thing I want to emphasize here with this map from Planck of the cosmic microwave background is that this is an actual picture, right? It's a photograph. The cameras may be weird, and it's not like the one you like have on your phone or like with an SLR, but this is an actual photograph that we've taken it's a snapshot of the universe when it was, if you take the age of the universe, 14 billion years old, and you put that in terms of like a human lifetime of 70 years, this is as if we took a baby picture of the universe when it was 1 day old. But again, this is an just honest-to-God photograph, right? And that's really powerful. And I'll talk about these things, but these large-scale fluctuations are what grew from quantum mechanical fluctuations in the early universe, and that will eventually evolve and form into all the structure today. Okay? But that's a snapshot of the universe when it was 1 day old. Just to put it in scale of the camera, these things are roughly to scale. And there is the Planck satellite, which costs roughly between 500 million and $1 billion, depending on how you count, and a Volkswagen Beetle, which my generation remembers. Probably Jim, have you ever owned a Beetle?
Yes.
How many?
1973, 2.
Nice.
One Beetle and one Sportback.
Nice. So yeah, well, these were like ubiquitous. This is the Honda Civic of like Jim's generation.
Kathy had one too.
So 3. So imagine that you take this and turn it into a camera and spin it around up in space. That's the thing taking the images of that sky. But basically what you see here is a roughly 1 meter diameter mirror, and then there's order of kind of dozens of bolometers that are cooled to 0.1 degrees above absolute zero. And it spins around the sky, but actually just makes that photo. And okay, so what are we looking at? That's just how you project the sphere onto 2 dimensions so you can look at it. It's the same as how we go from like a globe to a map, right? And there's different projections you can choose, but that's what we're looking at. So people are often, I think, confused about what exactly this is, but this is the radiation on the sky all around us. Now there's one other important caveat, which I wanted to make flat Earth jokes, but I'll keep going, is that we have to look through our galaxy, through our local universe. And so these are the kind of raw images at every frequency that Planck makes, okay? And you see here, what's the most obvious thing you see? Not a trick question. The line in the middle, what is it? What is it? No, yeah, you're right, what is it?
Milky Way.
The Milky Way, yeah, it's our own galaxy, okay? So we're taking a picture of our home, but we're trying to take a picture of the universe. So you need multiple frequencies, and then you build templates for what all the various components are, and then you're left with just the CMB, okay? So that's how that picture is actually made, but I'm giving you the more full disclosure of how that's made. And then you can also make different combinations of those frequency bands and higher level components, and you can look at things like cold clumps in the galaxy, so these are star-forming regions in our own galaxies. You can look at magnetic field lines in the galaxy. You can look at polarized dust. You can detect galaxy clusters. You can see polarized synchrotron. You can detect individual point sources. You can make maps of the gravitational lensing potential. You can even make line maps of our own galaxy in carbon monoxide, the second most abundant molecule in the universe. So these are all things, and this is just a snapshot of what you can do with CMB surveys. But the things you need are a lot of area, multi-frequency, and so forth. Okay, so I'm gonna switch gears a little bit and talk about what's happening on the ground. And a lot of what I do is revolved around working with the South Pole Telescope, shown here at the geographic South Pole. Here it is from looking at the Earth upside down, or whichever frame you want to be in. The reason we go to the South Pole is it's high elevation. It's basically the closest you can get to being in space without being in space. And that's nice because this telescope, which is 10-meter diameter, would be really expensive and difficult, and actually right today, impossible to get up into space. Okay? Remember that JWST, which is a 6.5 meter, cost $10 billion. And most of that cost was the engineering of making the thing unfold to fit in a 5-meter fairing. So, one day with big fairings, we could potentially just cheaply and easily get big telescopes like that up. But until then, it's kind of difficult. So South Pole, just to take home, it's the closest thing to being in space on the surface of the Earth. Okay? And there's some good things about it and bad things about it. Hard things about it, access is tricky. You can't just drive there. In fact, you have to take effectively military transport there, and it's only open for 3 months of the year. Okay? And so if you want to turn the lemons into lemonade, what that means is it's easy. You show up in LA, and the military gets you there. And it kind of makes you get everything working and then leave it alone for a year. So it's actually good. It puts us in a nice cadence and kind of makes us have our shit together. The great thing about it, too, is that you're at the geographic South Pole, so the sky is just going around and around. So you can pick one patch of sky that's clean and avoids the galaxy and just stare at it constantly, over and over. And that's great. Bad thing about it is that's the only sky you can see. You can't see the rest, so you're limited in how much area. And the great thing about logistic support when it's working and functioning, it's great. You show up like this, and they give you everything that you need, and you get down there. The not so great is when it's not working, you can't get there. And we're actually dealing with a lot of that now. So here's a human for scale. Spencer?
How often do you say it's not functioning?
Like the last decade?
Oh.
It's been tricky. Like basically there's a population problem, and then COVID messed everything up bad, and then it's been kind of, I would say, mismanaged, but also it's a really difficult situation to be in, and there's constraints from money and budgets. So it's certainly nothing money couldn't solve, but money's tight. Okay, so there's a human for scale, and you see this is kind of a weird telescope if you're used to looking at optical telescopes. First of all, it's been tuned for millimeter wavelengths, right? So we've actually degraded the surface of our panels so that it doesn't focus light from the sun and melt the boom. So that's why it doesn't look like a mirror to our eyes, right? And you also notice there's no struts in front of it. So this is an off-axis telescope, so it has a really clean, perfectly clean field of view and good control of our beam, which means good control of all the systematics so that we can measure large-scale modes in the sky. This is a cartoon. I PowerPointed this, but here's the telescope, and we pick one patch of sky and just scan over this over and over. Here's the kind of video of that. And that's all this thing does year-round. Okay. And this is the second generation survey that we made. This was done years ago. We were building the camera when I was a grad student. We were doing the survey when I was a postdoc. This image itself is now at least a decade old. But the new one is like even bigger and better, but it's hard to fit on the screen. So this is what things look like. And here it is compared to Planck. So here you see the spatial resolution of what you can get from the ground with a 10 meter compared to what you can get from the space with effectively a 1 meter. But this is the same exact patch of sky. And I just drew a line through it and put the things. But you see like the clumps match up. So you see when you go to higher resolution, you start to pick out point sources, which allows you to do astrophysics. And I'll talk about that next, or coming up. OK. We don't actually analyze most of this stuff by looking at the image. Usually everything's done by the power spectrum. So what that means is you take that map and you Fourier transform it. The way to think about that, or at least like I would think about it, is like think about your old stereo and you have base modes and frequency modes. And these are the low frequency base modes that are about 1 degree on the sky. So think kind of order of the full moon on the sky. And these are the treble modes. Think about it as smaller things, like the human resolution that we see at is 1 arc minute, and that's about 1 arc minute resolution, or 5 arc minutes. And the first thing to note, which is not, like if you ask me, we made a picture of the Big Bang, or the radiation left over from the Big Bang, or we made a baby picture of the universe when it was 1 day old, and we took the Fourier transform of it, what would that look like? Naively, I would probably think like, I don't know, like white, or maybe like 1 over F spectrum, but like noise. And instead, there's this structure, okay? And that means that the universe is ringing like a bell. And we can analyze those resonances and tell what it's made of. It's like a wind instrument, if you will. And we can analyze the position of that first peak, and that tells us that space is flat, or omega total equals 1. We can analyze the ratio of the first to the third peak, and that tells us how much, the damping term basically, like how much stuff is interacting with gravity and pulling it all in, or omega matter is what we call it. And then we can look at this damping term, and we can tell kind of the details of how that plasma in the early universe interacts effectively with itself. And we can do things like measure the matter power spectrum of the universe, the number of relativistic species, and the sum of the neutrino masses. So we can do things like that by basically looking at the large-scale structure distribution.
So, can I ask you? So, in that data, are those harmonics of omega t?
Are those not quite harmonics of omega t, but they're harmonics, yeah. So this is the power, right? So it's actually going like this, but then we square it.
Yeah.
Yeah.
And I just was wondering about where the peaks are. Are they equally spaced peaks?
Yes.
They look like they're equally spaced.
Yeah.
And you're saying that then represents something basic about the universe and not just. Oh, sorry.
It's on.
Is it on? Okay. Sorry.
And it tells us something fundamental about the universe.
And not about the aperture of the telescope.
The aperture of the telescope, the resolution elements are like way down here. So this is all resolved. And actually we've combined, what we've done here is these large modes. So you see SPT is all the points in yellow up to about there. And then these are Planck. So we've combined everything. But an important thing to note, which I didn't say, is see that line underneath it? That's not a fit to the data. That's our cosmological model. Mm-hmm. We literally just overplotted the data points here. So there's really good agreement to what we understand about the universe and what the measurements we make. And effectively, that's just because back at redshift of 1100, or when the universe was 1 day old or 100,000 human years old, it was just a plasma.
And
it was just a hydrogen sloshing around in a gravitational potential with...
And that model is too hard to explain in 20 minutes, I guess, right?
That's another...
That's a whole other course.
Yeah,
right?
that's kind of a whole other
Okay.
But it's just a plasma sloshing around. Okay. So what is this cosmology? And so that measurement, right, is kind of the cornerstone of our cosmological model. What is that cosmological model? This is called lambda cold dark matter. So what is cold dark matter? It's dark matter that's cold, meaning it has gravitationally collapsed. It's not going so fast that it can't collapse. And we don't know what it is, but we know it's dark and cold, and it builds all the structure in the universe. And how I think of like that structure is that it's the dark matter that's setting up. It's like the bones of all the matter, and all the gas and eventually stars and galaxies follow that gravitational potential that's set by the dark matter. And then what is lambda? This is the cosmological constant, or the dark energy. This is what's driving the expansion of the universe to accelerate. So not only is the universe expanding, but that expansion is accelerating. And it seems that space-time always wants to have constant energy density. So if you expand space, it has more space now, and so the pressure is greater, and that keeps happening and happening and happening. And it seems to violate like conservation of energy, and we have no idea why or what form this has or how it relates to the rest of the universe. But empirically, we can measure this. And we can measure it not just from the CMB, but all different kinds of ways that we can cross-check this and observe it, like in the distribution of galaxies. We can measure the expansion from supernova, like what Gotham does. So there's all different ways, and I'm not going to talk about any of those ways, but we're pretty sure about this model empirically. We don't know what it means, I would say, but we can measure it very well. And what's kind of weird to me is that the next decade is going to be us measuring this with more and more precision, but not necessarily adding any deeper insight. Right? And so what we need now is insight. But along the way, there's a whole bunch of other avenues that this is opening up and cool things that this CMB is allowing us to say about the universe. And so now I'm kind of pivoting to that. So let's think about that. So here's the same plot again. This is just power on the sky versus spherical harmonic on the sky. Okay? And here's full sky over there, 1 degree full moon size, and then 1 arc minute human resolution over here. And what I showed you before was the temperature fluctuations, the spectral distribution of the temperature fluctuations. Okay? There's also, at about the 10% level, those fluctuations are polarized. And this is just due to Thomson scattering. Basically, you have a hot spot, you get waves reflecting off of it, 10% of the light will be polarized. And that's shown here in power. And those modes will be a curl-free component, or a purely divergent term that we call EE modes, that we can break up into that. Okay? And this is just what we call this TT because it's temperature times power spectrum times temperature power spectrum power. And then this is EE mode, the divergent term. There's also a curl component that is induced in the early universe by inflation and basically space expanding rapidly, which is like gravitational waves, and imparts a polarization on that signal. Okay? And this is a purely curl term, which we call B modes. Okay? And so this measurement right here is kind of the holy grail in CMB measurements right now, because this is kind of one of the real tests that inflation happened in the universe, or early universe. So in other words, what happened in the first 10 to the minus 36 seconds of the universe. And a measurement of the amplitude of this tells us the energy scale at which that happened, which we parameterize as R, just the amplitude. And that tells us that not only did inflation occur, but when it occurred. Okay? And so this is, like early universe cosmology is kind of one of these holy grail measurements. and it happens in the first 10 to the minus 36 seconds. Basically, the quantum fluctuations in space-time were inflated rapidly as the universe underwent superluminal expansion. So the space itself actually expanded faster than the speed of light. And these fluctuations became the seeds of structure growth that is why we're here, like on a planet in a galaxy. And these primordial gravitational waves leave an imprint on the polarization of the CMB. So a measurement of this would tell us the energy scale of inflation, and this is a test of our understanding of gravity. And this is, a test and kind of a clue to the interaction between gravity and quantum mechanics. So, but this is all like another talk. Or actually, Peter Adshead gave the Astronomy on Tap last night basically about just this slide and talked for an hour on that, and we got maybe 10% of the way through.
Yeah, I had to leave early from that. But is there any alternative theory other than inflation?
Yes.
Okay, so somebody's thought of something that may.
They get even more crazy.
Oh, but they don't have the experimental evidence that this does, or it's still consistent.
Everything's still consistent.
Oh, I see.
Like basically in terms of lack of more evidence.
But it's crazier than inflation.
Inflation has already passed at least 3 really important tests, like the CMB being one of them.
Yeah.
So it's already kind of passed all scrutiny, but it is kind of, I would say, like ad hoc. Like then you can always ask, like, well, what comes before that? And there's like this field and blah blah blah. But right now we have not ruled out inflation, and it's not from lack of trying. Okay. So just putting this again, like the history of the universe in terms of human time scale. So here we are today. We're looking all the way across time and the observable universe to this time when we can observe the hot radiation left over from the Big Bang when the universe was equivalent of 1 day old in human time. And the next thing we're trying to do is go all the way back to inception, that 10 to the minus 36 seconds. There's other signals here. So one of the things that you can have are these EE modes that basically get turned into these curl modes in polarization, or curl B modes, by gravitational lensing along the line of sight. And so, it's similar. That's how you get curl terms, is by distorting space-time. And you can do that either from stretching it really fast or bending it from gravitational potential along the line of sight. And, if you're trying to measure these, that's a nuisance. But that's also a really interesting signal in its own right, because that's how we can take a picture of the distribution of dark matter across the entire sky. And so there's a lot of things we can do with that as well. So, and the lensing amplitude is also sensitive to the cosmic neutrino background, and it can constrain the masses of the neutrinos, which is really interesting for particle physics and cosmology. I really like neutrinos, so that's cool. And there's also another thing that can cause distortions, or another foreground, which is polarization in dust in our own Milky Way. And this was why, this was kind of the awkwardness of the BICEP result, that it looked like originally, 10 years ago, that this amplitude was abnormally high, but everybody was really excited about it, like it had been detected for the first time, and then realized, okay, now we understand polarization of the galaxy a little bit better, mainly because Planck finally released their data, but that's another foreground we have to deal with, and we deal with that by having more frequencies and very sensitive observations of large-scale modes and small-scale modes. Okay, so the point here is there's all kinds of things we can still do with the power spectrum, and we're measuring these things now, and we're planning and building the next generation thing that's going to do this even better. This is the current best limits on this are from the kind of sister experiments. This is South Pole Telescope. This is the BICEP experiment. This is an old photo, but we share a location at the South Pole. We share a lab space and building right here called the Dark Sector Lab. And we're working together now as kind of one team called the South Pole Observatory, where we analyze everything jointly. And these are actual constraints on the T modes, E modes, B modes. This is actually a little bit old, but they more or less look the same. Okay. So let's change a little bit. I'm going to change gears. We talked about cosmology and CMB. I'm going to talk about the other things you can do with these. And we're just going to zoom in here. Okay? And you see that these large-scale fluctuations, remember, that's real. That's the radiation left over from the Big Bang. And now, as you zoom in, you see there's other features, like these bright spots. And like 90% of those bright spots are radiation from basically black hole emission, or galaxies, but galaxies with supermassive black holes in them where the gas is trying to get in, and it gets in a traffic jam and caught up in magnetic fields, and it comes out in a jet. And when the jet's pointed right at you, we see it as a bright spot here. And then we see these dark spots, which are clusters of galaxies. And that's a whole other talk called the Sunyaev-Zeldovich effect. which basically casts a shadow or a spectral distortion on the CMB and allows you to detect these massive galaxies proportional to their mass, independent of redshift, which allows you to constrain dark energy. It's a whole other talk. I'm going to talk about 5% of these bright spots that are strongly lensed galaxies, going out to redshift 7 right now. Okay. First, one more stop along the way. What color is the universe? This is a plot of the color of the universe. This is the power on the sky at all wavelengths, from radio all the way up to gamma rays. And what's the brightest color? Where's the most power coming out? Yeah, microwaves. It's all that radiation left over from the Big Bang. It's the brightest thing on the sky by a huge amount, by orders of magnitude. Okay, that's how powerful that radiation is. What's the next brightest thing?
Why is ultraviolet not applicable?
It's there's no measurements there. It's not. I think it's not available.
Oh, okay.
Yeah, I didn't. The next brightest thing on the sky is all the radiation that's been put out across cosmic time by thermonuclear energy from gravitational collapse turning into stars, producing photons from thermonuclear reactions. That's all the entire history of all the stars that's ever been formed. And a little bit of the black hole emission, but that's like less than 10%. And this is called either the cosmic optical or infrared background, but it also encapsulates the entire history of cosmic star formation. And if there was no dust, it would all be optical light. It would be UV light redshifted into the optical. But the first measurements showed that half of that energy, half of the entire history of the universe, has been absorbed by dust and re-emitted here in the infrared. Okay? So and we can show that on one particular galaxy. This is just a spectral energy distribution of one galaxy, but you kind of see what's going on here. In the absence of dust, this is the emission you would get from the entire collection of stars within a galaxy. Okay? Then you throw in dust, which we know exists, and the spectrum, the UV light gets way down in emission, absorbed, and then it heats up the dust, and then the dust re-emits here in the infrared. And it peaks about 100 microns, which is why Alan Sandage, kind of the heir to Hubble, had this, what I think of as a famous quote, is that God lives at 100 microns. And the reason for that was twofold. One is that all this magic, all the light that's been observed, all the power that's been observed, is coming out at 100 microns. And they knew this just from the temperature of the interstellar medium. And the other thing is that at 100 microns, you can't see anything because of our atmosphere. So not only is like the entire history of the universe there at 100 microns, but we can't see it. It's in the heavens. You have to get above the atmosphere to even observe it. So that's part of the reason why. Yeah.
There was a Zoom question about the previous slide, I think.
Oh.
Why isn't the plot smooth at the boundary regions?
Smooth at the boundary. Flat? Zero? I don't know what that means. Why don't we save that for after?
Okay.
Okay. So cosmic dust, as a cosmologist, I used to literally roll up my eyes at the cosmic dust. Like I just wanted dust to go away. And the fact that I knew that there was some other subfield that was like all geeking out on dust, I was like, what? Just get that shit out of here, man. And then I started studying it. And I really like dust now. And I'm going to try to share my enthusiasm for dust with you on this one slide. So dust was first noticed about a century ago by astronomers attempting to understand the structure of the Milky Way. Like Herschel surmised about this. Shapley knew about this. They knew that the structure, the distribution of stars looked funny, and they assumed it was because of dust or something absorbing the light. It was really first kind of systematically studied by the IRAS satellite in 1983 that allowed the systematic study of dust in our galaxy and in nearby galaxies. The COBE satellite launched at basically the same time that I just showed you was the first one to detect fluctuations in the cosmic microwave background and measure the spectrum of the CMB and so forth. Also had another instrument on it called Derby. That's the thing that measured this stuff, that showed us that half of the cosmic optical background has been absorbed and re-emitted in the infrared. And so where does all this dust come from? The majority is produced by massive stars at the end of their lives, either by asymptotic giant branch stars. So stars go, as you know from stellar evolution, when they're done burning their hydrogen, they go through the phase where they're a red giant phase, and the phase after that is called the AGB branch. And basically, you get these like weird pulsations and dust forms in the atmosphere, and it kind of sheds it out. And then you can also get it from supernova remnants. And this is like actually a difficult physics problem, where a supernova is both creating dust and destroying it all. And so it's a complicated thing to measure exactly what's done and the proper fractions and all that. And there's also evolution versus redshift. So for instance, in the very early universe, you haven't had time for AGB stars to evolve yet. They typically take like 100 million years. So in the very early universe, you haven't had time, like above redshift 6, there has not been time for AGB stars to exist yet. So all of the dust could only have come from supernova. Whereas today, in the local universe, we think that about 90% of the dust is produced by AGB stars. The other point that I want to really drive home, and that we've said over and over, so half of the energy produced since the Big Bang has been absorbed and re-emitted by dust. Star formation always occurs behind dust. If you ever want to see how stars are being formed or how galaxies evolve, you have to look at the dust. Otherwise, all that light, half that light, and the majority of it is being blocked. And dust is a crucial constituent to the formation and evolution of literally everything, from planets to supermassive black holes and everything in between. It's also, you can think of it as the rise of complex chemistry, either in local regions like in a solar system or in the early universe. And some people think it may even be a catalyst for the ingredients necessary for life. So dust is the stuff. Dust is cool. Okay, we talked about that. And you can pick that apart, and you can make what I think of this as like a very, like basically a cosmology plot, although we often don't think of it like in terms of like one parameter that we often think of as cosmology. But this plot here, this is the plot of star formation rate density as the universe expands versus redshift or look-back time. And you see that the general picture is that over here at the beginning, more stars were being formed per cubic volume, more and more. It peaked around redshift 1 or 2, and then there was a decline. So what's happening is that gravity is forming galaxies, gas is flowing in, gas is being turned into stars, more stars are being formed per galaxy over time, and then and you reach some peak efficiency, and then it turns around more or less because the fuel for new stars, the gas, has been used up. It's already been converted into stars. And you can also take the integral of that, and this is the number of stars that have been formed over time. This is the stellar mass density, right? So at some level, this can only increase, right? Because you're just forming stars over time, and more or less those cores stay there forever. Big ones blow up and so forth, but those are actually small in terms of the total mass. And you can plot this on another way of looking at this. So there's a lot of corrections that go into this in systematics. This is a plot I made like over a decade ago when we were trying to plan a big telescope that was never funded in the end, even though it's highly recommended, lesson to young people. And this shows the direct observations from the ultraviolet. This is typically how we make this plot. And like things done by like the Galaxy satellite and Hubble Deep Field and Hubble telescope at high redshift. And then this is what can be done direct from the infrared. That's a direct measure of star formation rate that doesn't need to be corrected. So normally they measure this and then assume, oh, you need to make it like a 90% correction to correct for dust, and you move that up. And then these are the models. And these are kind of 3 I picked, but there's another 10 I could have put on there. The point of this is that there's about an order of magnitude discrepancy between these models everywhere from redshift 1 to redshift 8. And if you think about what's in that plot, or in one of those curves, it's the entire history of the evolution of the universe. It's all the gas, it's all the dark matter distributed, it's all the gas in there, it's all the galaxies, it's all the stars, okay, and all the physics that takes. And so it's not a surprise, I would say, that it's a difficult problem and they don't perfectly agree. What to me is cool is that if we make a good measurement of this, we're constraining cosmology, effectively. Or if you want to think about it not in terms of like a parameter, you're constraining all of the evolution of the universe or galaxy evolution. So I think of measuring this, over the next few decades is a fundamental plot in cosmology and astrophysics. One other really cool thing And this was the thing that got me excited about dust, like why I thought it was cool, and frankly, galaxies. So I just took here the spectral energy distribution for one galaxy. This happened to be like one of my favorite galaxies, ARP 220. And just imagine that you take a galaxy and you fix its luminosity like a light bulb. Okay? So now I'm calling this is 100 watts. Okay? And now I move this galaxy or light bulb away. The power is staying the same, but now I'm further away, so it's going to get dimmer by 1 over r squared, right? Okay. But then you also have the expansion of the universe, so that light's getting redshifted. Okay? And so now here I've just taken ARP 220, I fixed its luminosity like a light bulb, it's 100 watts, I've declared it to be 100 watts, and I've just moved it away and asked, what would I see? In other words, what would its flux be? What do we receive on the ground from this galaxy? And you see that as it gets further away, it gets dimmer faster than by the luminosity distance squared, okay? And it's also getting redshifted, it's moving this way. Okay, and another thing just to note, all of this you cannot see from the ground, you have to go to space. And there's this weird thing that's happening here between redshift 1 and 6 that I like to call magic. Sometimes it's called the negative K correction. But basically, I'm going to walk you through this. Instead of plotting wavelength versus flux, and then give a bunch of different redshifts, I'm going to pick one wavelength, and I'm going to ask, what is the flux versus redshift now at a given wavelength? Okay? Everybody with me? Hang on. Okay. So now we've got flux, so how much power we receive effectively, by distance for different wavelengths. So here you see in the near-infrared, Spitzer, and you see the flux from that galaxy is falling like a stone. It's falling faster than 1 over r squared. Whoops. Okay, because you're about here, okay, and you're going down the Wien side of this stellar blackbody. Okay, that's getting redshifted away from you. It's getting fainter faster than it should because of the shape of the color of the galaxy, effectively. Now let's look at what happens when you go on the Rayleigh-Jeans side of the spectrum, okay, of the blackbody from dust emission. And there you see that this galaxy is basically equally bright at all redshifts once you get above redshift 1. In fact, this is a log plot. So that means that if that light bulb, that 100-watt light bulb, appears brighter at redshift 6 all the way across the universe, when the universe was only 1 billion years old, as when it's effectively in our backyard at redshift 1, about halfway across the universe. Crazy, right? The other thing that you can immediately take from this is that if we can do a flux-limited survey, we can detect galaxies independent of their redshift, independent of distance, which is crazy powerful in astronomy, because usually we're limited by understanding the evolution of the galaxy, of the universe, because the farther away we look, the fainter those things are and the harder they are to see, right? But if we can do this, we can look at these galaxies and detect them no matter where they are in the history of the universe. Difficulty is now we can't tell the redshift, but we have ways around that, okay? So this is really cool, and people have known about this for years. I've heard that this was like the most popular test to use on the qualifying exam at Cambridge, and it was like kicking around there, and then people started actually like writing papers on this. I'm gonna skip over this. And the problem, though, is that technology's lagged. So there's this great effect you can use from basically observing the dust from galaxies. But it took a long time to develop that technology and make surveys sense enough to both make any sort of images and then map them on large scales. SPT was one of the first to do that on large scales, but we got lucky because some of those galaxies were strongly gravitationally lensed by intervening galaxies, which boosted their flux by about a factor of 10 and made it detectable in SPT. That was my thesis project, actually. Okay. So some of those sources were gravitationally lensed, and they were bright enough then that we did the first redshift survey with ALMA, right when ALMA turned on. This was like, ALMA was not even fully operational. It has 46 12-meter antennas now. At the time, we had 13, and they were still commissioning it and putting it all together, and they didn't even have all the instruments on it yet. But we did basically first light with ALMA with this when I was a postdoc. And this, after 10 years, is the result of that redshift survey. This is actual data across the 3-millimeter band in ALMA. And these lines right here that you see are all transitions of carbon monoxide, which is, I already stated, is the second most abundant molecule in the universe. And it has really bright lines, and it has a dipole transition, so you get a bright line every 115 gigahertz. And so if you measure any two lines, you get an unambiguous redshift. Okay? So we use that effect to target these galaxies that we found with SPT in this wide survey. With ALMA, this was about 20 minutes or 30 minutes each per source. And we determined the redshifts from the CO. And this took about a decade. It was not easy, but we finally completed the sources. And all the sources we found in SPT, we got a redshift for. And Cassie did the final survey paper in 2021. And that's all spectra there shown sorted by redshift. So here, this is sorted by observed frequency. Here, this is sorted by rest frequency. Okay? And you can see here, this is infrared luminosity. These are magnified, so that's the mu, just their gravitational lens. So this is the observed magnification versus redshift or temperature. So you see that there's an LT relation, right, just from Stefan Boltzmann law. And these are the unlensed sources. The SPT sources are up here just because they've been made brighter, but their temperature is the same. And then this is the SPT selection function. So this is just kind of the inverse of this curve, but instead of flux, it's asking what's our luminosity selection, and luminosity is proportional to star formation rate. So what's our star formation rate selection versus redshift? That's shown here. So that's our selection for SPT. These are all the things in our survey that we found in that first generation survey that ended like a decade ago. And Mel, who's online, is Mel there? Is working on the third generation survey of that, which I'll talk about. Okay. With that, we can then say, because we can detect these independent redshifts, and we made a sample, and we got a redshift for everything, we can say definitively when the first one was. And granted, this is a relatively massive galaxy, or these types of galaxies, but we can say with certainty that there are none above redshift 7 in the universe. And now, as we go deeper, we'll be able to, push this out and observe the onset of massive galaxy formation versus redshift over the next decade. This is what one of those blobs looks like in simulation. This is a simulation by Chris Hayward, who's going to be here next Friday, 2 Fridays? March 8th, 2 Fridays from now, to give a talk in this room. Another simulation showing these. So basically, these are massive galaxies in the process of being formed. Take your favorite, 4 Lyman break galaxies, slam them all together at once, and you get a submillimeter galaxy. These become the most massive galaxies in the universe today. This is an image of the most nearby counterpart, or equivalent of that, which is ARP-220. This is that SED I showed you before. This is an image with Hubble. The thing I like is here's an actual photograph with Hubble. There's the thing being simulated, and you see the correspondence. But that's what these actually look like. The cartoon of these things is that you have basically a bunch of fuel for new stars, and it's being funneled in gravitationally, and you get a burst of star formation at the core, and then that feedbacks, and then you get stuff merging on. But that's kind of what's going on, how these galaxies are being formed, how they're forming their stars. These are the most prodigious sites of star formation in the universe today. This is the highest redshift galaxy we have observed. This is 0311 at redshift 7. This is with ALMA. We can observe these with ALMA in a single line, like an IFU spectrometer, and so we can reconstruct it in 3 dimensions. And so this is that galaxy, just we're spinning around in 3 dimensions. This is the most detailed look at a galaxy in the epoch of reionization ever, period. And basically every one of these blobs is like a Lyman break galaxy, and these are all being kind of merging together into one super galaxy. We can also look at that galaxy with ALMA in molecular lines, and here's an image of that galaxy, granted at lower resolution, in water, in carbon monoxide, dust continuum, and higher J transitions of CO. Water's cool. We can also look at that galaxy at its isotopes. So we can do chemistry with this galaxy and probe basically how dust was formed and how the elements were being formed in the early universe, which is a probe of stellar evolution in the very early universe. This is still reducing this. This was one of those really problematic, we designed this observation as an experiment, even a null, we expected a null detection, and instead we got a 3 sigma noise blip. So it's been taking a long time to.
That 7 redshift, is that the maximum redshift that anyone's ever seen?
No.
And what is special about this one here that they were picked out to give you a maximum of 7? I see. 14, would that be
Why
the...
7 or the boundary above 6 is cool is because the universe was fundamentally different then. It was still neutral. So if you think about the beginning of time to today, the universe went from a plasma state, and when it converted from plasma to neutral, that's the surface of last scattering, that CMB that we see.
Yeah, the CMB.
Then it was neutral. Then it went through a phase where the first stars turned on and made a bunch of UV photons that re-ionized all the hydrogen. And that ended around redshift 6. So that phase between redshift 30 maybe and 6 is what we call the epoch of reionization, when the first things were turning on.
And then what would the redshift of the cosmic microwave background be?
1100.
1100,
Yeah.
okay.
But it goes weirdly linear with, it's not linear with time.
Okay, I've got to go now.
Okay. Oh, but this is
The best part?
no, but this is the question you just asked.
Okay.
So redshift, so this is a plot of the most, not counting the CMB, the most distant object we've seen versus time and the method that we found it at. And so that source I just showed you was redshift 7, okay, which in the optical, because optical photons are cheap, dime a dozen, silicon's cheap, easy to make. That's typically where the redshift frontier is done with optical photons. And so we're a decade behind in terms of detecting these things from the DESTA mission, but this shows you most distant astronomical objects. So we're about redshift 12 now with JWST. Yeah, but the reason it's significant is it's in that epoch of reionization.
Okay.
You can go now.
All right, thanks.
You should say, this is all bullshit, and slam the door. Oh, here's what I just said in a nice picture. Okay. I want to put a few pieces together now. And I got a thing at 1, I guess. But you guys can leave if you need to. We're coming up to the end. Think about if you had to pick one number to characterize a galaxy or summarize all of its properties, what one number, value, observable, would you pick for a galaxy? Brightness. What else? Mass. What kind of mass? Okay. Tony gets an A. I also would pick stellar mass. Now you might say like a theorist might say it's dark matter halo mass. I think that gets really messy because what about when you're in clusters and so forth? But stellar mass is usually observable. It's basically, to first order, its brightness with its distance, okay, corrected for its distance. So both of you were kind of right, I would say. And how do you do that? You measure its brightness at about 1 micron in photometry, and you measure its stellar mass. The second number I would say, if I wanted to know, would be its rate of change. Okay, so we think of stellar mass as how many stars that galaxy formed. And the next thing I'd want to know is just what's the rate of change of that number, the derivative. And this is me thinking like a physicist, not an astronomer. But how do you do that? You can do it directly from the UV. We've heard the caveats about dust absorption. Typically, people do this with H-alpha emission, so hydrogen emission. Also, Passion alpha is been opened up recently with JWST, and that's what Kadar is. Kadar's not here. You might be online. This is Kadar's thesis. You can do this with ionized carbon, water, and so forth. There's a bunch of ways of doing that. The next thing I would want to measure is its potential to form new stars, star formation potential. That's its gas mass. That's how much stuff there is that can eventually be turned into stars. And when that's all fueled up, that's it. So that, to me, are the kind of 3 main things I want to do. Of course, when you have astronomers in the room, then you have, okay, what about its black hole? And it clearly has some role with the environment and evolution of the galaxy. There's also, it's sitting in a dark matter halo, and there's large-scale structure around. And there's also all kinds of other details like its metallicity and its ionization and its morphology and the environment and so forth. But if how I think of this is like, what are the 3 fundamental measurements that I'd like to know about other galaxy? That's kind of what I think about it. And what are the tools we would need to measure those 3 things? So here we have where is it? Stellar mass, star formation rate, the derivative, and gas mass, the potential. And we can measure those, like the gas mass and star formation rate, we can measure with ALMA. JWST can give us the stellar mass for the first time for these high redshift galaxies and also give us measurement handle on the star formation rate. So now we can measure that rate of change with 2 independent surveys and compare them. And we can put all these things together to really get a view of what's happening in galaxies. The typical important observables are the ratios between these things. So like it's stellar mass divided by gas mass divided by someone else's gas fraction, which is like how much fuel is there. It's specific star formation rate, basically how many stars is it forming per unit star. So how fast is it, what's its current normalized burn rate. And then its depletion time, how fast, given its burn rate and how much gas it has left, how soon will that burst of star formation be over? So, this used to be kind of hypothetical, like one day we will have JWST. That was the status from when I was a grad student and while I was kind of perpetually like a year away. But now we actually have it. And we wrote a proposal to be the first people to use JWST and point these at SPT sources. This is called templates. I'm going to skip this, but this is all work by Kadar. One cool thing about it is we got to be the first people to use JWST, and we even got paid to do it. Bad thing was that we had to do a bunch of work, and we had to wait around a long time. And the data were public immediately, so you get some asshole on like Reddit, like, look what I found. Like, it was just sitting there. It was like, no shit, we pointed at it. But that's fine. That was fine. So these are all the 4 templates. We picked 2 sources that were discovered in the optical with the Sloan survey and were lensed by gravitational clusters. And then we picked 2 that were discovered by dust emission from the SPT survey and were lensed by galaxies. So that's kind of what we saw. This is the rogues gallery of those 4. JWST is also an IFU, so we can make 3D pictures of these. So these are images or moment 0 maps, so line maps of that line, in this case H alpha and Paschen alpha of those galaxies, of those 4. And you see, this is at like a lot of the first images from JWST that you saw, you're like, whoa! That was easy, low-hanging fruit of nearby things to make pretty pictures. Here, we're really pushing the limits of what it can do. And that was kind of the point of this. Why they gave us this time was we were exercising all the modes of the observatory and doing it like at the very limit of what it could do. And it could only do that because of the aid of gravitational lensing. This is an image of one of these galaxies. Just full disclosure, we've moved the foreground galaxy that sits there. And you see an optical with NIRCam is shown in the color image, and our ALMA high-resolution ionized carbon map is shown there, just for comparison. We can like basically deconvolve the lensing, and so we can make an image of the source with as if before it was lensed. This is work by Jared Cathy at University of Florida, but this is what that galaxy looks like from our lens model. And you see that it's a merger. So that's probably what's making it form stars so quickly and prodigiously. This shows you just of that same galaxy, all the observations we have in H alpha and Paschen alpha, and also the smallest dust grains, effectively, PAHs, which you can think they're carbonaceous grains, little rings. This is like the stuff from barbecue smoke or car exhaust, but I like to think of it as kind of the smallest molecule of dust, or the first really complex molecule typically observed in the universe. And this was the most distant detection of that molecule, and it was resolved in the galaxy for the first time. And you see, it's pretty rowdy. This is marginal. This was like, a few hours of the JWST, but this is the type of thing it can be doing, over the next 10, 20 years. This is the Rogues galaxy. So for that program, we observed 2 sources, but then we've been proposing and proposing and proposing. So now this isn't even all of them. We have about 10 that have been observed. This is the first 8. And here's the big image is near CAM, and this is MIRI, the mid-infrared. Okay, so all of that was from the first generation SPT survey, and like a small fraction of all the things we did. Like I didn't really talk about galaxy clusters and large-scale structure stuff and all that. That was just the first generation survey where we had about 100 galaxies going out to about redshift 7. The current data that we have in our hand and reduced in the form of a catalog, which Mel is leading, that survey is about 5 times deeper, and instead of finding one source at redshift 7, we should have hundreds above redshift 7. This is a model in red of galaxy evolution. It's not even a predictive model, it's a postdiction, meaning they take all of the counts and galaxies that we know about, and then make a model to make a prediction. Okay, so it's a post-diction. It's like, here's everything we've ever observed in the universe. I'm going to tune up my model to fit that, and then I'm going to use that model to predict what we can see if we observe more galaxies. And you see there's good agreement there with what we observed in gray. And so we take that model and then just ask what is in the survey that we have in our hand now in that catalog. You see that instead of 100 sources we found with first generation SPT, we should have about 10,000 of those high redshift dusty sources. And instead of going out to redshift 7, it should go out to redshift 9. And to me, what's cool about this is not only are we going to have like hundreds of these kinds of sources, or thousands, or tens of thousands. That's all of the stuff that we know for sure. So we observed it. There's all this other room for discovery, which is really fun and really neat and really exciting. This is just a random 100 square degrees of the current generation survey with and we have 3 bands, 3 colors, and so all the sources are color-coded. The point is here, we have a shit ton of sources, and we need to sift through them all to go find those interesting high redshift ones. So that's going to be the work of like the next 10 years, or maybe grad students in this room. Okay. Also, I'm gonna skip all. I'm at the hour, so I'm gonna skip all time domain stuff. And Yuji's work and the movie. I'll show you one movie. Yuji's making about that. That was a balloon. Ignore that one. But this is a map Yuji's making. We're spending about a month a year pointing SPT at our galaxy. Normally, we'd go to great pains to avoid our galaxy, but we had a month where we couldn't look at our deep fields because of the sun. So we argued and argued and argued and finally got SPT to agree to point it at the galaxy, which may seem crazy, but we were looking for transients. And that's a balloon, but that's what is going on now. I'm going to skip CMBS4. I wanted to talk about intensity mapping in TIM, but I'm out of time. Maybe I'll do this.
3 slides for astronomy on tap, but 132.
This isn't Astronomy on Tap. And it's my seminar at my center. So yeah, I'll do what I want. Okay. I'm gonna end with one point here. There's always been this synergy or team up in astronomy between smaller telescopes that survey the whole sky and find interesting objects, and big telescopes that study those interesting objects in great detail, usually with spectroscopy. Okay, I think the early example of this was like the Schmidt 48-inch telescope that did a photographic survey over the entire sky with northern survey, but then they did an equivalent one in the south. And the Hale 200-inch, which was the most powerful optical telescope, most impressive telescope ever built for basically 50 years. And in the more modern era, when you could have computers to set mirror surfaces and silicon to make CCDs, we had the Sloan Digital Sky Survey, which was a 2.5 meter telescope surveying basically all of the northern sky. And then the twin Keck, or 10 meter class telescopes. Here I'm just showing Keck, but that was the first, but there were others. In Hawaii that were following up these sources with great detail and determining redshifts and really studying the rarest, most interesting objects in great detail. The next decade, we have a wide field survey. Now, our small telescope is the 8.4 meter Rubin Observatory that's going to be surveying all of the southern sky. And just for scale, that's about $1 billion class. And we have between 1 and 3 extremely large optical telescopes, ELT, GMT, TMT, from about 2030. These are all like way more than $1 billion each. But so we have this in the optical. What is the equivalent in the millimeter? Or at the wavelengths where you understand the star formation rate and the gas reservoir and star formation potential and hidden history of star formation? We don't have one. And there have been a few proposals. From a decade ago, there was a thing called CCAT, which was highly recommended but not built fundamentally. There were some proposals in the last decadal review as well. The Europeans are doing a study. So there's like ideas of it, but we don't have that yet. And at some level, one can argue like South Pole telescopes sort of did that role. But there's a lot of phase space here for interesting science. I think if we could do a submillimeter survey, they could be commensurate with like LSST. And I think, why would we want to do that? If you think about what was the big breakthrough in how we understood our universe was understanding how stars burned. And there's this funny anecdote. Everything I talked about with the cosmology, do you know when we knew that the universe was expanding? What year? Anybody? Grad students? Hit me. What year did we know the universe was expanding?
1929.
Nailed it. 1929. What year did we figure out how stars burned? 1934. So all this cosmology was old, right? Like the fact that we're living in this evolving universe. And something that we kind of, as a cosmologist, take for granted, like, yeah, stars, like the point mass things. That's a harder problem. But a crucial step and insight in understanding the lives of stars was this Hertzsprung-Russell diagram, which just put them in terms of basically temperature and luminosity in a plot, and we can now sort them out and eventually make sense of how they evolve. And what is the equivalent of this plot for galaxy evolution? Do we have a Hertzsprung-Russell diagram for galaxy evolution? The one plot that we can put up and be, now we understand how all the galaxies, why they look like that, and how they've evolved and what they're going to become. Do we have that? Why not? Well, it's a little bit messier, I would say. But also, I don't think we have all the ingredients quite yet. And I think what we need is, we need to probe the stellar mass of galaxies across time, and we need to probe the gas mass and star formation rate of galaxies across all of cosmic time. And that, I think, is how we build that kind of HR diagram of galaxy evolution. And what's cool is that in the coming decade, we more or less have the instruments we need, the facilities we need to probe the stellar mass, and that's LSST, WFIRST, Euclid, that are all about to be observing. Some Euclid already is. And I think, we have ALMA, and what we need next is that wide field survey to probe everything else. And I think that's how we're going to make that HR diagram for galaxy evolution. So I'd like to thank my group. You saw a lot of their plots today. This is us a year ago or so, fall, I guess. The South Pole Telescope team, this is the team back in 2007 that built everything. This is what they look like now. You see we've kind of grown. We've, like gremlins, somebody got us wet. And then this is the group studying just the submillimeter galaxies that I talked about. This is the JWST team. This is the TIM team. I didn't talk about intensity mapping. We can talk about intensity mapping next. And TIM. And this is the CAPS group here at NCSA. OK, that's all I had. Thanks.